America's newest entry in the program of the exploration of the space above our Earth and the investigation of the planets of our solar system and beyond is the Apollo Saturn IB. With the successful firing of this space transportation system, the National Aeronautics and Space Administration has added an intermediate space vehicle to its family of 3 Saturn launch vehicles. The Apollo Saturn IB, standing over 20 stories high, will be the first Saturn to be used for manned flights. It initially will be used for practice and training for the manned lunar mission to be accomplished before the end of the 1960s with the much larger Saturn V booster. The earlier Saturn, the Saturn I, has completed its flight schedule of 10 firings, scoring an unprecedented success by proving 100% successful in all flights. The Saturn IB first stage, while appearing to be almost identical to the earlier Saturn first stage, is actually a much improved booster. The cluster of 8 engines was increased in power from 1.5 million pounds thrust to 1.6 million. The weight of the booster was reduced by 20,000 pounds, thus giving the Saturn IB a significant increase in performance while retaining the reliability factor which the smaller Saturn has so dramatically shown in actual flight. The second stage of the Saturn IB has more than double the power of the earlier Saturn second stage. This part alone is as tall as a 5-story building. It will later be used as the third stage of the Saturn V. To complete the space vehicle, an instrument unit is added which contains the guidance equipment necessary to place the Saturn on its planned flight path. Above this is the payload, a command and propulsion module and a lunar module, the spacecraft which later will be boosted to the moon by the larger Saturn V to perform the actual manned lunar landing. The story of this enormous Saturn IB began in 1962 when the National Aeronautics and Space Administration determined to test the complete Apollo spacecraft in Earth orbit as soon as possible. This Saturn would permit manned Earth orbital rendezvous flights to begin a year earlier than previously planned without the expense of a completely new development program. At the Michoud Assembly Facility at New Orleans, the Chrysler Corporation, under the direction of the Marshall Space Flight Center, started production of the booster stage. Using fabrication and assembly equipment similar to that used for the earlier Saturn, the booster began to take shape. The cluster of tanks first was assembled, the 8 uprated engines added, and the intricate engine controls and the electrical network were installed. With assembly completed, detailed quality checks and tests were conducted on the propulsion, electrical, control, instrumentation, and telemetry systems. A central computer complex supported the operation. The booster was next moved on its transporter to the barge Palaemon to start its long trip up the Mississippi, Ohio, and Tennessee rivers to the ground firing site at Huntsville, Alabama. In March 1965, the stage was in the stand at Huntsville, ready for the static firing. It was fired first for 30 seconds, then 2 weeks later fired for the full flight duration of 2½ minutes. Engine control was tested by gimbaling the engines during firing. All recorded results indicated the stage was ready for its maiden flight. It was then barged to Michoud Assembly Facility for final checks and later to Cape Kennedy, where the NASA Kennedy Space Center team began launch preparations. At the same time the booster was being assembled, The second stage was under fabrication at Huntington Beach, California by the Douglas Aircraft Company under direction of the Marshall Center. This completely new hydrogen-fueled upper stage uses a single 200,000-pound thrust J2 engine. Among the unique features of this stage is the use of a common bulkhead to separate the liquid oxygen from the liquid hydrogen fuel. Special insulation on the bulkhead keeps the liquid oxygen from being frozen by the liquid hydrogen, which has a temperature of 423 degrees below zero. The stage was later moved to the Sacramento Test Center for its pre-flight test firing. A full-duration firing of 7½ minutes marked the first time that a fully automatic system had been used to perform a complete checkout, propellant loading, and static firing test on a space vehicle. This engine was also programmed to gimbal in simulation of the guidance commands it would receive in actual flight. After final checkout, the stage was transported by barge from California to the Kennedy Space Center, where flight preparations were underway. Meanwhile, the instrument unit, the brain or nerve center of the Saturn vehicle, was under joint development by the International Business Machine Corporation and the Marshall Center at Huntsville, Alabama. This unit provides the commands for engine gimbaling, in-flight sequencing of the engine propulsion system, staging operations, telemetry, and all primary timing signals. The Saturn IB instrument unit is essentially the same instrument section which will be used on later Saturn V launch vehicles. The complete payload for the Saturn IB space vehicle was developed by North American Aviation under the direction of NASA's Manned Spacecraft Center, Houston, Texas. For the first Apollo Saturn IB flight, this consisted of the command module, the propulsion module, a weight simulating the lunar module, and the launch escape system. Upon completion of the first flight payload, the sections were transported to the launch center for addition to the booster. Before a final development work on both stages and the payload, a complete non-flight version of the full Apollo Saturn IB vehicle had been placed in a 204-foot-high dynamic test stand at Huntsville. Here, the full rocket was subjected to shake tests for determining its vibration and bending characteristics. In keeping with the new NASA policy of flying complete Saturn vehicles beginning with the first flight, the vehicle we have seen under development was planned to follow this concept. Both stages and the instrument unit were scheduled for a full test in flight. The command module was complete except for the life support system, and the propulsion module was set to fire its propulsion and guidance system. This first launch vehicle was programmed to perform a suborbital lob shot with the Apollo command and propulsion modules as the payload. They were to be lofted to an altitude of approximately 300 miles by the two booster stages. After the first stage burns and drops away, the second stage burns for 7½ minutes. Then its attitude controls tilt the payload to the proper re-entry position. This stage is kicked aside and the command and propulsion modules coast over the apex of the flight path. Small rockets fire to seat the liquid propellants, and the propulsion module engine ignites to increase the re-entry speed. The engine reignites to check the restart capability and further increase the speed. Attitude rockets then turn the command module for re-entry. The propulsion module is kicked aside and the Apollo continues toward the thicker air at a speed of nearly 18,000 miles an hour. This mission was planned to provide a major test of the Apollo heat shield at a high re-entry heating rate and to demonstrate the operation of the propulsion module system and other spacecraft functions, including the recovery system. The cover of the Apollo separates, and the main parachutes open at 2 miles above the water to land the test payload in the ocean without damage. Navy ships stood ready in the recovery area with equipment to raise the capsule aboard ship for the return. Later tests would evaluate the success of the re-entry maneuver. 2 motion picture cameras were prepared for installation on the Saturn first stage to provide a permanent visual record of the separation sequence of the second stage from the first stage in flight. They were also set to show the operation of the liquid hydrogen-fueled engine. The cameras were attached to the first stage, and a system was installed to eject them at the appropriate time. Soon after ejection, spring-loaded flaps open to stabilize the cameras and to slow their descent. They re-enter the atmosphere at 7,900 miles an hour. 3 miles above the ocean, a paraballoon fills with gas to expand the balloon. The attached parachute and the balloon produce drag to reduce the capsule impact velocity to prevent capsule damage. The paraballoon also serves as a location aid and floats the camera in the ocean. Upon contact with the water, a fluorescent dye is released to aid recovery. A shark repellent is also released to ward off marine life that could damage the capsule and paraballoon float. A radio beacon attached to the top of the paraballoon transmits a signal to aid recovery planes and ships in the area. The film would be returned to Huntsville, Alabama for study. As the firing time approached, 190,000 gallons of liquid oxygen, liquid hydrogen, and kerosene were poured into the tanks. The countdown proceeded toward the moment of ignition. The firing team made final checks and evaluations. A successful firing would mean that the United States Apollo-Saturn program for the conquest of the moon and beyond was proceeding as planned. 5, 4, 3, 2, 1, ignition. The Apollo-Saturn IB lifted slowly at first, then doubled and redoubled its speed. On into the distance it flew. The first stage completed its mission. The onboard camera showed the successful separation of the first stage, the burn of the small solid rockets to seat the liquid propellant in the second stage, and second stage ignition. Telemetered information to ground stations revealed the success of the second stage and the propulsion module. The Apollo-Saturn IB had performed its planned mission. With this success, the National Aeronautics and Space Administration has completed another step on the way to the moon.